In one room, a patient breathes evenly, comfortably asleep, while a surgeon operates. In another, a bomb squad in heavy Kevlar secures a dusty bottle of clear liquid, treating it like a live grenade ready to shatter. These two radically different scenarios are driven by the exact same class of chemical compounds, ethers. They are reliable medical tools, but if left on a shelf exposed to light and air, they slowly degrade into highly explosive peroxides. To understand this contradiction, we look back. The introduction of ether as an anesthetic shifted surgery from a desperate race against a patient's pain to a controlled clinical environment, allowing for previously impossible levels of surgical precision. Because early ether was highly volatile, it was often delivered through simple metal inhalers like this one. The liquid rapidly turned into a gas, filling the patient's lungs, and frequently escaping into the air of the surgical theater. That ability to instantly vaporize and the tendency to quietly build explosive pressure both originate from the same place, a deceptively simple molecular architecture. At its core, an ether is an oxygen atom acting as a bridge between two alkyl or aryl groups. Chemists refer to this general framework as the ROR-chyme structure. Under the formal IUPAC system, we name these compounds as alkoxyalkanes. For example, if we attach a methyl group to both sides of the oxygen bridge, we get methoxymethane, commonly known as dimethyl ether. If the groups on either side of the bridge are identical, it's a simple or symmetrical ether. But if we swap one of those out for an ethyl group, we create methoxyethane. This asymmetry makes it a mixed ether. So how does sandwiching a single oxygen atom between two carbon chains dictate the physical reality of the entire molecule? Oxygen has a higher electronegativity than carbon. It pulls electron density toward the center of the molecule, creating a polar carbon-oxygen bond bent at an angle of roughly 111 degrees. But here is the critical constraint. With no hydrogen attached directly to the oxygen bridge, ethers cannot form hydrogen bonds with other ether molecules. They are structurally isolated from one another. This comparison table shows exactly how that isolation plays out in the physical world. Notice the massive gap in boiling points. Dimethyl ether boils at a freezing 248 Kelvin, while ethanol, an alcohol of similar mass that can hydrogen bond, doesn't boil until 351 Kelvin. There is one exception to this isolation. While ethers ignore each other, their central oxygen bridge can accept hydrogen bonds from water molecules, which gives them a slight solubility in aqueous solutions. This unique geometry, polar but unable to stick to itself, makes ethers lightweight, volatile liquids. They are primed to escape into the air, which explains their adoption as the first widely used inhaled anesthetics. To build this specific ROR structure in a lab, chemists rely heavily on a method known as the Williamson synthesis. Looking at this general equation, we can see the mechanism in action. It's an SN2 reaction, where a sodium alkoxide attacks an alkyl halide, forging the new oxygen-carbon bond and leaving a salt as a byproduct. This method has strict physical limits. It works best with primary alkyl halides. If you try to use secondary or tertiary halides, the molecule is simply too crowded. The reactants bump into each other, leading to elimination rather than successful substitution. On an industrial scale, chemists use a different approach. They take primary alcohols and force an intermolecular dehydration using concentrated sulfuric acid, holding the mixture at exactly 413 Kelvin to produce the ether. Creating an ether requires forcing specific molecules together under tight, highly controlled conditions. But once formed, that chemical bridge is remarkably stable. Ethers are famous for their chemical inertness. They ignore bases, oxidizing agents, and most metals. To break the bridge, you need a powerful weapon, specifically strong acids like hydroiodic or hydrobromic acid. The acid strikes first by protonating the ether oxygen. This makes the molecule vulnerable to an SN2 attack. A halide ion, like iodide, attacks the less hindered carbon and splits the molecule into an alkyl iodide and an alcohol. If you flood the reaction with an excess of hydroiodic acid, it doesn't stop there. That remaining alcohol fragment is forcefully converted into a second alkyl iodide. Which brings us back to our bomb squad. When ethers are neglected, prolonged exposure to ambient air triggers radical reactions. Oxygen slowly worms its way into the structure, degrading the stable ether into peroxide compounds. The oxygen bridge is strong, but its stability is conditional. Expose it to extreme chemical stress or years of environmental neglect, and it breaks with dangerous, explosive force. The oxygen bridge takes on different properties when it connects to a benzene ring. This creates an aromatic ether, with the most common example being anisole or methoxybenzene. In this configuration, the methoxy group acts as a powerful activator. It pushes its own electron density down into the aromatic ring. This nitration pathway shows the structural outcome of that activation. By feeding electrons into the ring, the methoxy group strictly directs incoming electrophiles to attach at either the ortho or para positions. In aromatic ethers, that oxygen bridge actively pushes electron density around the ring, determining where and how the molecule will react with its environment. When scaled to an industrial level, these chemical properties translate into a versatile set of tools for large-scale manufacturing. Because they are polar but chemically inert, compounds like diethyl ether are effective solvents. They provide a stable environment for complex chemical extractions and highly sensitive Grignard reactions to take place without interfering. Thanks to their specific directing properties, they also serve as vital chemical intermediates, acting as the building blocks for many modern pharmaceuticals. The theoretical physics of the ROR bond scales up to create the foundational tools required for modern organic synthesis. Ethers prove that you don't need complex, sprawling molecules to generate powerful chemistry. But that power comes with an absolute rule. If you work with ethers, you always test for peroxides before use and store them with a chemical stabilizer.